Okay, so I think it's almost 4. I'll just wait for a few minutes and then we'll start the class. Okay, so before we start with this week's content, just want you to comment on the last week's question where we were talking about the kinked demand curves. And let me stop this actually. So we were talking about different types of kinks in the demand, sorry, not in the demand curve, in the budget curve. And we were solving some questions where, the demand function is, sorry, again, not demand function, the budget function is varying based on the quantity the person is purchasing. So let me just open this one link. I added this as a link in your class note, the class slides also for week 4. Let me just share here. A minute. Okay, 1 second. So I'm just sharing this link here also. You can visit it on your own time. And I hope you can see the screen. So I've just shared my screen. It has one web page. I hope you can see that. You can just type in the chat box if you can. So this is an interactive visualization of those similar kind of questions what we were discussing last time about the budget set. So if you see here, you can actually change these values, the budget, how you can see how the budget set is changing with changing the available income and with changing the slabs. So here X hat is like the inflection point where there are several slabs in electricity pricing. And if you see, like, you can see how the budget set is changing with changing the value at which the electricity pricing is changing. Similarly, you can alter the pricing. You can call it P low and P high. That's what they've called it. So see if the pricing is very low, then for these particular values, there is no kink in the budget curve. But if the pricing, if the pricing, the low value itself is very high, then obviously there's no kink. And if it is low, then the slope of the curve is changing. And similarly for this, as the pricing is increasing, you can see it's getting more and more steep. So you can just play around with these variables and you can see how the budget set is getting adjusted based on that. Similarly, this is the other type of kink in the budget curve where you have vouchers instead of just money. We took an example of this type also last time. So in this again, you can see how these values are changing, and you can alter the curve between gift card and cash, and you can see how um, you're losing a certain possibility of the budget set by giving a gift card or a voucher instead of money. This is the quantity discount, which is a value. I mean, it's a type of a question we had discussed last time, although not in too much detail. But yeah, so you can see how the dotted line is showing the initial budget set, and the new green area is the final budget set. So this is, I just found this site and I thought it was a really good resource for anybody studying this thing. So this link is there in the previous week's lecture slides. If you want, you can refer to it. And I'll also drop the link here in the chat. So you can refer to it now also if you want. So on the NPTEL portal, now they have updated the link where you can get all the class slides and the recorded videos. I don't know if you've noticed, there is in the sidebar right at the bottom, there is a link which says TA sessions, TA live sessions, something like that. So over there, they have updated. If you open that spreadsheet, in that spreadsheet, you have the whole list of weekly videos and weekly class slides and class notes. Okay, so the second thing, last time somebody had asked me a question at the end of the class, and I had solved one question and the second question was remaining. And I went over that question, but that question is incomplete, or that question is not very properly defined. So that's why I'm not solving that question. But if I get time, then next week I will reframe that question and I will define the variables and I can try and solve it then. I didn't get enough time this time. But the problem with the question is that they've not defined the variables. They've given the answer in terms of some variables which they have not defined. So I don't really know what they're talking about. They've used some variable called S2S, and I don't know what is S in that question. So, so it could be a good question if it was properly defined, but it's not. Okay, so any other questions from the previous weeks, you can tell me now before I get started with this week's content. No? Okay. Okay, so I'll start with, oops, I think I'm logged off here. Okay, just give me a moment. Let me just share this. Okay, so this week we will be discussing utility in great detail. And before we get to the whole, the utility function and how we maximize for utility, there are a few things we need to first understand. Where does this utility function even come from, right? So when we were talking about preferences, I think we just very briefly touched upon preferences in one of the early videos. So we need to understand that utility function is not like usual functions which we encounter in maths, like fx is equal to some function of x and y, even though we write it in the same way. But the utility function is a function which gives you a basic measure of how happy somebody would be with given circumstances. Very loosely defining it would be that So, for example, like when you say, I have this much money, you're talking about something very concrete. You're talking about 10 rupees, 15 rupees, something like that, right? But when you say that, if I get an orange or an apple, that makes me happy, or that fulfills some requirement I may be having. We're not talking about an exact number, right? We're talking about how much you like an apple versus an orange, which is a slightly abstract thing. So what we need to do in utility is we need to define something, some measures or some criteria using which we can make utility function as close to a normal kind of a function as possible, right? And that is what we refer to as a preference relation. Okay, so what we mean by a preference relation, this is basically in the domain of set theory, is that you have like a whole set of things, say a set of basket of fruits, and in that basket of fruits, you should be able to rank all items in that basket in a certain order of preference, right? Like you can be like, okay, I like orange almost, not almost, I like orange the same as an apple, but you have to be consistent in your ranking. And what we mean by that, I'll just come to that. But that is one of the most important criteria in defining a utility function, and we'll come to the utility function shortly too in today's class itself. So let's start with that ranking, what I was talking about, because that preference relation is the is the basic fundamental idea which we're trying to concretize or crystallize through the utility function, right? The utility function is a formal mathematical relation which kind of describes that preference relation. Okay, so now say suppose there's this guy Joey. He has three options. One is a melon, the other is an apple, and next is the orange. So he says that he likes melon better than orange, apple better than melon, and orange better than apple. So he has given a certain preference criteria for his choices. And now the question is, which axiom of rationality do his choices violate? So now we have to come to something called axioms of rationality. So when we are defining a preference relation in mathematical terms, that is, a preference relation is a very proper mathematical thing. It's like I said, it's something in set theory, or something even very fundamentally what we use in calculus, right? So when we are defining a preference relation, any preference relation has to follow three axioms of rationality. And what are those three axioms? They're actually on the screen. They are reflexivity, completeness, and transitivity. So all this is already discussed in your lecture videos. So I don't really want to repeat everything in the lecture videos. But in this particular criteria, which axiom of rationality do you think is getting violated? Or are like all of these criteria getting violated, or none of them? You can, if you think nothing is getting violated, you can tell me that also. What do you think is happening? You can write your answer in the chat box if you like. So let's write this in this way. Okay, somebody has answered. Okay, let me write down the relation first, whatever information is given. So we're writing Joey's preferences, and the question says, let me open the question. Let's say the choices are between melon, apple, and orange. Okay, I'm just using one letter things instead of like writing down the whole thing. It just goes faster. So what does he say? He says he likes melon better than orange. This is not a greater sign. This is a preferred to sign. It's something like this. Okay, it's not a greater than sign. They both look very similar, but and it's sometimes a bit difficult to differentiate between two. But just letting you know that this is a preferred to sign, not a greater than sign. So he likes melon better than orange, and apple better than melon, and orange better than apple. So now we want to rank these three in a certain order. That is the idea, right? That is what we mean by a preference criteria, preference relation. So if we try to rank these, what happens? So melon is better than orange, apple is better than melon. Okay, this is not very good. Apple is better than melon. But now we are again saying that orange is better than apple. So that means this is becoming like one circle. You cannot rank them. They're like going in a merry-go-round, right? So whenever this thing happens, when the preferences are sort of circular rather than in one order, then you cannot actually rank them. There is no possible ranking, because if we give this 1, this 2, this 3, then this again goes back here and this becomes 4, right? We cannot rank them. We cannot give them any kind of ranking. And hence, the principle which is getting violated is transitivity. Now, why is completeness and reflexivity not violated? Does anyone want to answer? What do we mean by completeness or reflexivity getting violated, by the way? Let's say, what would happen if completeness was violated? If we had another fruit here, say banana. Okay, this is too thick, 1 minute. Say suppose we had another fruit here, banana, okay? In the fruit basket, he also has a banana, but no preference is defined for banana, right? We don't know whether Joey likes banana at all or not, or if he hates it, if he likes it more than something else. We don't know anything about bananas. So then if that were the case, then we would say that completeness is getting violated, because one of the items in the consumption set does not have any ranking, and that is not possible in a well-defined preference relation. Yes, it's complete because we have a relation defined between each of these items which are there in the consumption set. If there are items in the consumption set which do not have any kind of a relation defined on them, then we say that completeness is violated. And completeness is a mandatory or a compulsory criteria for rational preferences, right? Reflexivity is usually not violated because, when we say reflexivity, what we mean is that, Joey likes orange as much as orange, something like that. Or Joey is indifferent between orange and orange, which is which is just saying that, he likes orange, something like that. It's very kind of difficult to define reflexivity in mathematical terms, or sorry, not mathematical, in intuitive terms, because we don't normally think that way. But in set theory, reflexivity simply means that the item is kind of related to itself. That's basically what reflexivity means. So reflexivity is rarely going to get violated. And if a particular set has completeness criteria is fulfilled, like it's not violating completeness, then you can be sure that reflexivity is also not getting violated. Okay, so this answers this question. So this is like a much simpler question. I will come back to a slightly more complex version of this question a bit later. For now, we will move to more mathematical treatment of preferences. So like I said earlier, that when we are talking about the utility function, we are basically trying to mathematically describe the amount of happiness you get from consuming some goods. And like, based on the limitations of the technology of our times, at present, we can only visualize sort of like a preference relation between two goods. Like, you can define a utility function for any number of goods, but it's very difficult to visualize it beyond 3 dimensions. Even in 3 dimensions, it's not so easy to draw it or so easy to intuitively understand what is happening in that diagram. Right. So, which is why almost all the functions you find at your level are going to be for like just x and y, or x1 and x2, something like that. But all this, whatever mathematical logic and all the, whatever axioms of rationality, preferences, whatever we studied, it holds for any number of goods. It's just that we cannot visualize any number of goods. So utility function is only going to be for two variables, but it works. The logic works for any number of goods. You'll just have to develop a slightly more sophisticated mathematical expression for dealing with those things, and usually work with vectors when it comes to multiple goods. But anyway, that's not what we are discussing today. So there are two goods, x and y, and you can assume, I've not defined it here, but let's say x is ice cream and y is say x is ice cream and y is what, chocolate. Okay, so x is defining ice cream, y is defining chocolate, and we are given a set of possibilities for the utility function, and you're asked that if she likes both of these items equally, which of the possible functions given is going to be her utility function. So you can take a few minutes to think if you want, and if you want, you can answer. Okay. Anybody else wants to try? So let's look at the logic for this type of a question. How do we define these type of questions? So when we say she likes both the goods equally, what we are saying is that she will be willing to give up, say, an epsilon amount of x to gain an epsilon amount of y without any change in her utility, right? Because if she has consumed, say, x1 plus y1 in one consumption set, say this is consumption set A, or let me put the comma here, and another consumption set is x1 minus epsilon and y1 plus epsilon, then both these consumption sets give her the same amount of utility because she values both an equal amount. So if she's losing x1 by a small quantity, epsilon, but she's gaining another good by the same quantity, she will be equally happy, right? That's what we're trying to say here. And hence, which function do you think is more likely to capture this phenomena? What we're saying is u of x1 comma y1 is equal to u of x1 minus epsilon y1 plus epsilon, something like that. I mean, I've just written it mathematically. Intuitively, it just means that if you lose a certain quantity of good 1 and you gain the same quantity of good 2, your utility is going to remain the same. Now, just mathematically speaking, if you have an equation like x plus y is equal to k, and here you write x minus epsilon and y plus epsilon, you still get k, right? Minus plus gets cancelled, just mathematically speaking. So therefore, you can just say that their preference relation is going to be straight line, and it has that -1 slope, right? And the different values of k which you get for all these straight lines give you different levels of utility, but along any one straight line the utility is constant. So this you can say u is equal to, say, k1, here u is equal to k2, u is equal to k3, and it's increasing in this direction because you always want to have more of both the goods. Is this making sense? Any questions in this? If you want, you can test this even graphically, like here, from here till here, and you can see, okay, my drawing is not perfect, but you are losing this much and you're gaining this much, and your utility is remaining the same. It is still the same equation. So the correct option is u is equal to x plus y. I think that is one of the options, right? U xy is equal to x plus y. That is the correct option. Even if you just see mathematically, if in any of these other functions you alter the value of x and y by the same amount, like x minus epsilon, y plus epsilon, you will not get the same function back. It will be a different function, right? So the first option will be the answer. And a related question with this same yes, it implies that she will be happy, because we are only speaking in mathematical terms. Remember, that's why I said that utility is something we have mathematically defined to capture your preferences and how sort of happy one good versus the other good is making you, right? It's not a strict number in that way. It's an ordinal number. It's not a cardinal number. Cardinal means that the number 2 is, if you write 2, 3, 4, that is different from writing 4, 6, 8, right? Ordinal is when, if you rank some numbers, some values as 2, 3, 4, and if you rank another set of values as 4, 6, 8, the ranking is still the same. So there's no difference. But in a cardinal number, the number is not just your ranking, but it is also holding a certain value, right? The value of the number matters, not just the ranking. But in utility, we are only referring to an ordinal value, which means that all we are saying is that if you take away one good and if you gain same quantity in another good, the utilities remain the same in this particular scenario, not always. Okay, somebody typed something, but I don't see the message. I'm not sure what you asked, but if you can retype your message, because I don't see a message there. Okay, so in this question, the next question is, what are her indifference curves like? And what do you think is going to be the answer? So what are indifference curves? Indifference curves are, you can say they can be a curve or a line on which the value of utility is the same along the curve. So we already drew the indifference curves actually. Okay, let me. Shoot. So we have already drawn the indifference curves. These values, these lines which I drew, u is equal to k1, u is equal to k2, u is equal to k3. These are nothing but indifference curves, right? So in this case, actually, these are just straight lines. So you could think of them as convex, or you may think of them as not convex, because in this particular case, the person is indifferent between certain like combinations of x and y versus just x versus just y, right?
Ma'am,
So
can
that
I?
happens rarely. Yeah, somebody wants to speak.
Yes, ma'am. Can I answer the question? It is
Okay.
convex to origin, I think, because downward sloping, convex to origin because the marginal rate of substitution.
Your voice is breaking actually. Can you repeat that?
Uh, the answer of the question is convex to origin,
And why is that?
just because marginal rate of substitution, downward sloping.
No, that is not how you will always decide convex to origin. So, okay, let me address the what you just said. Just give me a few minutes. I'm explaining that. So, what we mean by convex to origin is firstly whether the preferences are convex. And so you have to understand firstly there are three different contexts in which we can use the word convexity, and you have to be very careful about what is being asked in the question. And these are
Yes.
completely mathematical terms, so I'm not going to confuse you by talking too much about it, but I will talk about it since you mentioned it. First is curvature. When there is a curve and you're talking about curvature of the curve alone, nothing mathematical, like a lens, it can be convex or it can be concave, right? That is just curvature. But that is not what we are talking about when we talk about, uh, second, I think, yeah, my screen got disconnected. I will connect it again. Just give me a moment. I do want the diagram on the screen, otherwise it will not make sense. Okay, so the first thing is the curvature of a curve, right? Of like a lens. We talk about convex and concave lenses, right? But that is not what we're talking about here. Then there are two other things. One is a function. A function can be convex or concave or quasi-concave, right? That is a slightly more mathematically rigorous term. And that's why I don't want to talk about it. But just if you want to know, the utility function must be quasi-concave. It can be concave, but that is something which is not, I don't think it's there at your level, so I'm not going to talk about it. The third thing, which is what we will talk about mostly, is the preferences being convex, which means a set, any set. When you're talking about set theory, a certain set being convex or not convex. There is no such thing as a concave set. It is only convex or not convex. Okay, so in this particular context, when we say convex to origin, we're talking about whether it is whether the preferences are convex or not, and which, if they are convex, are they turning towards the origin or away from the origin? That's the complete question. I mean, if it helps, I can rephrase the question to make it a little clearer for you, but that is what we are referring to. Now, in the case of a straight line, as you can just see visually, it is neither turning this way nor turning that way. Let me draw another diagram which will probably answer your doubt a little better. And whatever you, I think you may have studied about MRS decreasing and stuff like that, we will come to that. But it's not that all downward sloping curves will be convex. That is not true. And we'll just see how that is not true, because downward sloping can be in different ways. And depending on which side the utility is increasing, the preferences may or may not be convex. So if your indifference curves are like this and your utility is increasing in this direction, then if you join any 2 points on this curve or any other curve, then this line is still in your consumption set. It is still on the side of the increase, right? Any point on this blue line is preferred to any point on the pink curve, right? That is because utility is increasing in the direction of the green arrow. So let me shade this part. So if you see, any area above this pink curve, just ignore that slight shading which has gone below it. Any area above that pink curve is more preferred than the lowest pink curve, right? If you call this, say, U is equal to K1, right? Any area on the right hand side, right upper hand side of this pink curve is more preferred, which means that this blue line, which is joining any 2 points on this pink curve, is more preferred than any point on the pink curve, right? This is just, I'm just speaking visually from the graph. I've not discussed anything very complicated so far, right? So when we talk about convex preferences, what we mean is that a combination of two bundles is always more preferred than just one bundle alone or one good alone. So like good A and good B don't have a very balanced proportion of the two goods, right? This is X, this is Y. Then B has more of X and very little of Y, and A has a lot of Y and very little of X, right? So any point on this blue line is going to be a little more balanced than A and B, the consumption bundles. And that is always going to be more preferred than too much of one good or too much of the other. That is what convexity means in preferences. Okay. And the geometric way of checking whether it is convex or not is this, that if you join 2 points on the indifference curve, the points on that line segment should be on the side of utility being more or higher, not less. So in this case, if I just invert this, arrow, and if I make the arrow the other way around, see, I make the arrow go this way, and utility is increasing in the opposite direction, then it will not be convex. You understand? Which is why just the slope of the curve alone is not the deciding criteria of whether preferences are convex or not. You have to be careful about which side the line segment is falling on when it comes to increasing and decreasing of utility. Okay, so now in this case, in our case, it's just a line fragment, right? And in this particular scenario, in which case, which by the way is a case of perfect substitutes, as the it would be self-explanatory. You can substitute any amount of X for any amount of Y. In this particular case, it so happens that the person is absolutely indifferent between X and Y because they're perfect substitutes. So whether you have too much of one good or too little of the other or a combination, they're indifferent between that. So you wouldn't strictly call it as convex, but if you say that this is convex because you know the line segment is still falling on the same line, you won't, probably you would still get marks for it. I don't know, depends on the teacher. So if you join 2 points on this line, say suppose, then you know this line segment also falls on the line, right? So it's not more preferred, but it's also not less preferred. It's just as preferred as the 2 points. This is A and B. This is something in between. You getting what I'm saying? Because this is a straight line, right? So the line is overlapping with the straight line. So I would say the answer is none of the above. But if you say convex, most probably if the teacher is generous, they will still give you the marks. Okay. But more importantly, it is like, I hope you understand the way you decide whether some preferences are convex or not, because just the shape of the curve alone does not tell you that. You have to be careful about which direction utility is increasing or decreasing. And we will do some more questions of this type. Okay, so this is a different type of a curve. And I will give you a few minutes to think over this question. So these are Molly's preferences over milk and cookies. And you can see the direction of the arrow. The arrow is showing the direction of increase of utility, okay? The black arrow. Now you have to see which of these options is not true. You can answer which is true or you can answer which is not true, whichever way you like. So I'll mute myself for a few minutes. Also, as you can probably see, I still have a cough. So I'll let you think for a few minutes and you can type in your answers in the chat box and then we'll discuss it. Okay, I think most of you have attempted the question by now. So, okay, let me see what the question is. 1 minute. Yeah. Um, all right, let's see which one of these is going to be the answer. This is question number what? 1 minute. 4. Okay. All right. So let's draw the let's draw the diagram. So something like this, and preferences are increasing in this direction. This is cookies. This is milk. Okay. So what do we see is happening in this, which is different from most of the cases we've taken before? First thing we see is that utility is increasing towards origin instead of away from origin, right? When utility is increasing towards origin means the lesser she has of both the goods, the happier she is, right? So maybe she is some kid who does not like milk and cookies. That is the only way your preferences will increase in this way, right? If you want, this is how I do it. When you're given a direction of the increase or decrease, increase of utility, you just decompose this arrow into its horizontal and vertical components, vector addition. This is the vector split, right? If you add the left and the horizontal and vertical arrows, you get this arrow, which means that utility is increasing as you decrease cookies and as you decrease milk, right? This is what it means, which means that she does not really like milk or cookies. She's like, she has to consume both because her parents are making her, but she doesn't actually like them, right? So she's happier without milk and without cookies. So at the same time, we also see that her preferences are not a straight line, right? They're not a straight line. There are some curve. We don't know what the function defining those curves is, but it is definitely not a straight line. That much we can easily see, right? From just the diagram itself. We don't need to investigate a whole lot for it. So that means that, as we just saw in one of the previous questions, that the case of perfect substitutes in which the person, the consumer, prefers both goods exactly the same comes out to be a straight line, right? We just saw that in the previous question. So in this case, that is not happening. We don't see a straight line, which means that she does not prefer milk and cookies exactly the same. There is some variation. See, if you see the curvature of the of the indifference curves, you see that this is 1 point. You can see this is maybe 1 point. This is another point. So utility is increasing in this way. So she hates a combination of milk and cookies even more than just milk and just cookies, because this combination part, you can say, or let me do it the other way, not with this curve. Let me draw a line and explain it that way, because this way we can make a mistake. Okay, let's redo this. So for instance, we take 1 point here, 1 point here. Okay, in these two bundles, let's say this is A and this is B, right? And we join it like we did in a straight line. Let's move B a little bit. Okay. Oops, sorry. Let's just redraw this line. Assume this is the line that I want to draw, that B is just this point, okay? And this line segment is it falling on the side of increase of utility or decrease of utility? It's on the side of increase of utility, right? I hope that that would be obvious. See, this segment is higher utility than all the area behind it because arrow is pointing this side, right? I'm sort of just approximately shading it. Okay, which means that this line segment, which, well, it was supposed to be pink, but now it's blue because I merged it with cyan. So this line segment is on the side of higher utility. So are the preferences going to be convex? Yes, right? Preferences will be convex, even though this is a strange kind of a graph where, the person is sort of not liking either good too much. Like if she is consuming it, she's becoming unhappy. But the mathematical constructs which we used to define all this, they still hold, right? And in within those mathematical constructs, we see that, what I said earlier, you can scratch that in this case, we actually see visually that a combination of the two goods is actually more preferred than not two goods, two bundles. A combination of two bundles is more preferred than either bundle, which is the basic criteria of convexity of preferences. So yes, preferences are convex in this particular case, right? Now, let me see what the other options are in this question. So first is preferences are convex. So that is true. Next is Molly likes both milk and cookies equally. That we just said cannot happen because for that, the indifference curves would have to be a straight line. Then is an increase in consumption of milk and cookies increases her happiness. That is also not true because, as you can see, an increase in consumption is decreasing her happiness. And D is Molly prefers a combination of milk and cookies to only milk and only cookies. This is also true, actually. And that is what I was just discussing. Because only milk and only cookies is on the side of the lower utility. A combination of the two, if you want, you can stretch this curve a little bit more, this side and this side, right? And if you want, you can draw another line like this, right? The green line where it cuts the x-axis and where it cuts the y-axis is where Molly is consuming only milk and only cookies, right? And any point on the green line segment is a combination of milk and cookies. And you can see that it is actually on the side of higher utility because the arrow is going in this direction. So let me redraw this arrow so that it's a bit clearer. So does this make sense now? A combination of the two is actually preferred to just milk and just cookies, even when we're talking about her disliking both. Okay, any questions? So I hope you have answered A and D as what is correct rather than what is not correct. Yes, combination is preferred. Now, the question actually asks which statements is not true.
Not
So
true. Yes, ma'am. Molly likes both milk and cookies equally is the correct correct one, I think. The answer.
why would it be equally? Why do you
Mm,
think Molly likes milk and cookies equally will be correct?
Not correct. It's incorrect, ma'am.
Yes.
Question is
Yes.
asking not true. So B is the
Yes,
answer.
no, I was not asking you. I was asking other people who have answered A, B, and A and D. I was just asking that. Hope you have answered what is. I was asking if you answer what is correct or what is incorrect. You have already said what is incorrect.
Yes, ma'am.
Yeah. Okay, so I hope it's clear. That's the main thing, whatever we've discussed so far. Okay, so I'll move on to the next question. Okay, so this is a question where you have to draw the preference curves rather than interpret. Okay, KG Krishna, you asked something. You're saying because it is curve. Okay, so you're just answering what I was saying before. All right. Okay, so in this question, we are told that Rachel likes pizza but hates Coke. Okay, and consuming pizza makes her happier, whereas consuming Coke makes her unhappy. Assume pizza is on the x-axis and Coke is on the y-axis, then what do you think her indifference curves would look like? It's just to understand whether you got the concept or not of how you draw indifference curves. So the curve itself can be of different types. That is up to you. But what is possible? What can be some possible indifference curves to show her preferences? That is the question. So upward sloping and downward sloping mm, doesn't really answer the question. If you can, I don't know if it's possible, but if you can just draw it and share a picture in this chat box if you like. Otherwise, you can just draw it and keep it, and then when we discuss it, you can check how it looks. So I'll give you a few minutes to think.
I'm, I think I don't, I can draw this, but the curve will be upward sloping rather than
So
downward.
that's what I said. Upward and downward sloping doesn't carry much meaning when you're talking about indifference curves because you have to draw several things in that. So instead of answering, please draw it and keep
Okay.
it with you. If you want, you can share a picture of your drawing in the chat box. Otherwise, just draw it and keep it, and then you can check it when we discuss it.
Okay, ma'am.
Okay, so I think you've had some time to think over it. Mm, Let's do this one by one. Okay. This is pizza and this is Coke. You're told to put pizza on x-axis and Coke on the y-axis. Right. So now I will do what I explained earlier. I will first draw arrows showing the direction of utility increase with respect to each good. Okay. So first of all, we are given that she likes pizza. Pizza makes her happy, which means more of pizza means more utility, right? So for pizza, direction of utility is like this: more is better. In the case of Coke, she does not like Coke, and consuming Coke makes her unhappy. Means more Coke means less utility. So less Coke means more. So the direction for Coke is downwards, right? So far, so good. Because less Coke is making her happy and more pizza is making her happy. So I've just drawn the arrows for X and Y axes. You can, if you want, you can draw it directly if that's easy for you. But I'm just decomposing it. Okay, good. Somebody has shared it. And you can draw it directly if you like that. But I'm just showing you the process by which you can draw any indifference diagram given how somebody likes or dislikes the two goods. Now, if you do vector addition of these two, it becomes like this, right? So this arrow, the tangential arrow, is the direction of increase of utility for this particular combination of goods. So it's not horizontal. So now that means that we can now draw the diagram, right? So this curves can be something like this, and utility is increasing in this direction. Or because we are not given exactly in what kind of a combination she prefers them, we're just told that she likes this and she does not like that. We're not told whether they are um, equally preferred or disliked or what. So we don't know exact curvature of the indifference diagrams, but we do know in which direction they will be sloping and in which direction the utility will be increasing. So it can also be like this. If they are perfect substitutes, except that pizza is a good and Coke is a bad, then in this case also utility is increasing in this direction. These are, you can see, 45-degree lines. Okay, so the curve, the curve type of curve can be anything. I think we're also not told whether preference is a convex or not. Yeah, we are not told. So that means, again, it can be some other type of shape also. Let's say it's like this, but it's bending the other way. Utility is still increasing in this direction. All of these would be valid. That's why I asked you to draw it, because only when you draw it, you know that it's not really about upward sloping and downward sloping. It can slope in whichever way, but the direction of utility increases in this direction, which is kind of more important. Okay, so any questions in this particular question? Any doubts? I mean, okay, so if we were given that preferences are convex, then only this one would be correct. Line is not really considered like convex in that sense, and the other one is definitely not convex. So if we were told that her preferences are convex, then the first diagram would be the only correct diagram. But we are not told that. So any of these three could be the correct answer. Okay, now the next question is sort of similar to the first question, in which you are told that a consumer has a consumption set like so for two goods. You have A, B, C, D belonging to the real positive number set, and the preferences she has mentioned are as below. So this is slightly, like I said, it's a slightly more complex variation of the previous question. So the same question, which axiom is violated? And I want you to spend a little bit of time thinking over it and then tell me which one is violated and why. Why is also important, because, just, I don't want you to just guess. So I'll let you think for a few minutes and then we'll discuss it. Okay, let's solve this question. I think most of you have had enough time to solve it. Okay, let's see. I also don't remember the answer. We will solve it now. Let me open the question. Okay, so we are given, let's just first write down what all we are given. We are given that the consumption set is, so she's consuming two goods at a time, and what she's consuming, like the consumption set is given as, okay, so these are the consumption bundles. Um, what did you say? Okay, I have not solved it. I mean, I solved it before, but I don't remember the answer. So we'll solve it now. Okay, now we are given the relations, the preference relations, like so. So I'm just writing down what is in the, I don't know how to write this symbol properly. Okay, so this symbol means it is A comma B is more preferred to B comma C, or the person is indifferent between A, B, and B, C. So this symbol means they're indifferent between the two choices. Okay, then we are given B comma C is less preferred to A comma C. B, D is same as D comma A. Oops, the hell. Okay, yeah, D comma A is strictly preferred to A comma C, and B comma C is strictly preferred to D comma A. Now we will try to rank these so that only when we rank we can check whether they are all kind of um, you know lining up nicely or not. So first let's see if we have defined a relation between all of these. We are given 5 bundles, right? A, B, B, C, A, C, B, D, and D, A, right? Let's first see if each of these is actually being used up or not. A, B is there, B, C is there, A, C is there, B, D is there, and D, A is there. So all the 5 bundles are actually used. Okay. Between A, B, and AC. Okay, I don't think that is how you decide, but that is why you have a preference. Okay, I'll come back to that question of completeness. After we rank, we will know whether we are missing some information or we have all of it. That is how we'll know whether it is complete or not. Okay, so let's start with what we are given. So we put AB here, and we know that AB is, well, let me put it on a horizontal line. I think it's better that way. Okay, so let's do AB, and we know AB is preferred to BC, and BC is, so let's say this is the direction of preference, increase. Okay, BC is less preferred to AC. So AC should come somewhere here before BC. And we know that BD is more preferred to DA. We don't know anything else about DA. I'm erasing this text just so we have more space. BD and DA are the same. Then we have DA is better than AC. So DA will come on this side. It is strictly better than AC. And DA and BD are the same. And BC is strictly better than DA. Okay, which means we are in a spot of trouble, I think, right? We start with AB, which is better than BC, and then we find out that AC is better than BC. And then we move on to BD and DA, which are indifferent, and DA, this is DA, is better than AC. So you see, DA is better than AC here, but DA is less preferred to BC. So here we have a little bit of trouble, right? Because DA is better than AC and AC is better than BC. This is how we should have it. This has a indifferent also. So this is how we get from one part of the relations, and the other part we are getting something like BC is actually referred to DA, this last part. Here this says BC is preferred, strictly preferred to DA, which means we are going around in circles, right? Is that making sense, what we just did? This part says that BC is preferred to DA, whereas if we combine the first 3-4 steps, we get this relation that DA is preferred to BC, DA is preferred to AC, and AC is preferred to BC, which means DA is strictly preferred to BC. So both cannot be true at the same time. DA cannot be strictly preferred to BC, and BC is also strictly preferred to DA. So transitivity is definitely violated. And let's see about completeness. Is there any information missing with which we can rank all 5 of them? Because if there is some relation, see, if you have transitivity, then if you are given a relation between them in pairs of 2, you can always find the relation between the remaining, right? If you're given a connection between AB and BC and between BC and BD, from transitivity you can get the relation between AB and BD. But if transitivity is violated, then you may not be able to come to such a conclusion. So let's see if we have a relation between all of them. Let me open the question once again. Right. So I think only you're getting a relation between all the others, but because transitivity is violated, you cannot really say anything about completeness. You getting me? Because if transitivity were not violated, I think completeness would also not be violated. So you have BD relating to DA, and BD is not relating to anything else. Okay, and DA is relating to BC and AC, and AC is relating to BC, BC is relating to AB. So this part, we know BD is as preferred as DA, and we know DA is preferred to AC, and it is less preferred to BC. But if this sign were opposite, we would have completeness, because then you can rank all of them and then you can map a relation between all of them. But because this part is getting violated, we also do not have completeness. Is this making sense? Yes, no, maybe. The main purpose of completeness is that there should be a relation between each item and some other item. So there should be a relation between each item and other items in the consumption set. So if there was another item here, say D, C, and this is the given preference, then we know for sure that completeness is violated because DC is not there in the mapping at all somewhere, right? But here that is not the case. Here all the five are there in the mapping, but the mapping itself is not following transitivity. So therefore, see, the whole purpose of transitivity is that if you have, say, okay, why isn't this working? Oh, shoot. Just please give me a minute. Somehow my pencil has suddenly stopped working. Okay, now it's working. Yeah. So say suppose you have, say, five elements, okay, A, B, C, D, E in this consumption set. Now, if you can neatly rank A, B, C, D, E like this, then if you know the relation between A and B and you know all the other relations, then you also know the relation between A and E, right? If no trans, in this case, in some other cases, it may be a different, setup, because set theory tends to be kind of complicated. So I'm not saying that if transitivity is not violated, completeness will always not be violated. That's not true. Like I said, in this case, even if you had transitivity, but if you had another element here, DC, completeness would be violated, right? But in this case, that is not true, because in this case you cannot, you are given a preference relation. Each member of the set is being used in the preference relation, but you cannot establish a relation between that particular member and every other member. You understand? So you are given a relation between, say, BC and AC, right? But because you are cannot establish transitivity, you cannot use the given preferences to establish a relation between BC and all other members other than AC, right? Completeness means there should be a mapping between all members of the set. In this case, that is not happening. You understanding? Because transitivity is not allowing you to rank them in this kind of a way. So in some other cases, there may be something else complicated. It's possible transitivity is violated without completeness being violated. It can be possible that completeness is violated without transitivity being violated. It can be anything in a general case. In this particular question, is what I'm trying to answer here. That, if you had transitivity, you would not have had violation of completeness also. Okay, so in this case, you can say that completeness is also violated. Because the whole purpose of this whole preference relation itself is that you can put every item with respect to all other items. That's what we mean by completeness and transitivity. That if you have a certain bunch of possible goods for consumption, you should be able to give all of them a ranking. One member should not be left out, or it cannot be that one member is ranked only with respect to two members and not with respect to the other 50 members, because then you cannot define a utility function for that, or a preference function for that, right? That is what we mean by completeness. And when we say transitivity, we mean, like, all of them are ranked and we can use that relation to map other relations. So in this case, that is not happening, which means that this person's preferences are not rational as per our definition of rationality. Okay, so let's move on to a slightly different aspect of the utility function. So Sherlock's utility for consumption of two goods is given by the function u a comma b, where a and b are the two goods. And John observes Sherlock's utility function and defines his own utility function as VAB equal to alpha plus UA comma B whole square, where alpha is a positive constant. So in this case, which of the following will be true? I'll let you think. Okay, others? Anyone else? I'll let you think a bit. Okay, so let's see what happens in this particular example. Question 7. So we have, let's say US is equal to UAB. This is Sherlock's utility. And let's say UJ is equal to VAB. This is John's utility, which is alpha plus UAB whole square. Okay, where alpha is greater than 0. So this is where the whole concept of ordinal versus cardinal aspect of utility functions comes into play. So in this case, they have different utility functions, but their ranking or their preferences are going to be like pretty much the same, like their ranking of goods, or let me use the words which is used here. Same ordering over consumption bundles, that is the proper term. They have the same ordering over consumption bundles, and that is because if you do something called a monotonic transformation of in the case of negative utility. So let's assume that we are not talking about negative utility, because generally you will not deal with those kind of scenarios where utility is negative. And that is why we kind of uphold any kind of positive monotonic transformations of the utility function. Because like, yeah, in slightly more advanced um, cases, there may be negative utility. But if you see, we have been using only one quadrant for drawing all our utility and indifference curve diagrams, right? That is because we are not considering cases where utility is negative. And in most cases, even like so-called negative utility can again just be redefined to be positive, right? Negative and positive is again not like a it's not like a mathematically rigorous definition, right? What we define as zero utility is eventually up to us. Hence, what we define as negative utility is also up to us. So, that's why I keep emphasizing that utility is an ordinal ranking. It's not a cardinal ranking. So instead of -1, if you define it to be, you can slide it to the right without making any difference to the ordering of consumption bundles. You get what I mean? So that is why we have only considered cases where utility is positive. So even when we were, say, talking about utility decreasing, we have not gone to cases where utility is negative. We're only talking about it increasing versus decreasing, right? Okay, so that said, let me just also write this. Assume utility is always positive. And you can also assume this to be true for pretty much the rest of your course. You will not encounter cases where utility is negative for this exact reason, because we don't define it to be in that way. Okay, so then, which is why if you see like any positive monotonic transformation of the utility function gives another utility function which has the same ordering of all the consumption bundles. So not just monotonic, let's say positive monotonic. You can test it if you want. A utility function, let's say. I think all this is covered in your lectures, but maybe not in excessive detail. So you can get questions like of all different types just on this particular concept. Let me take a few more examples here. So in this case, the utility function u is first squared. Square is a positive monotonic transformation. Then you're adding a positive constant alpha to it. And that is also a positive monotonic transformation. Now, if you want, you can, you can define this function and see how it works out. You can take some example. Let me see, I had taken one example last time. Okay, so let's if assume that u comma b is a into b. Okay, these are the two goods, a into b. Therefore, v VAB is equal to alpha plus AB whole square. So now let's just take some values of A and B and see what we get as the values of utility for John and for Sherlock. So let's say A is equal to 1, B is equal to 1. Let's say alpha is equal to 5. Okay. U is equal to 1. VAB is equal to 5 plus 1 is equal to 6. Then let's say A is equal to 2, B is equal to 3. And you can play with numbers, that's like up to you. This is 2 into 3, 6. VA comma B is equal to 5 plus this is what, 6 square, 36, this is 41. And you can keep adding whatever you like to this. A is equal to 3, B is equal to 1. So the basic idea is that they will follow the same order, right? Here you have 1, then 6, then 3. So you see 1, then 6 is greater than 1, then 3, which is lesser than 6, but greater than 1. And in the second one also, you have the same ordering, 6, then 41, then 14, which is 14 is less than 41, but greater than 6, right? So the order ranking of consumption bundles is the same in both. That is all we're trying to say. The value of the utility function is going to be different because we have obviously done some transformation. It's not the same utility function, but it is going to give the same kind of ordering over the consumption bundles, which is what we are actually concerned about, at least in this question. So let me take a few more examples and you can tell me whether this that is going to be a positive monotonic transformation or not. So let's say, suppose this is a bonus question, u xy. Say suppose u xy is equal to x, what we just took, xy, or 1 minute. Yeah, let's say u xy is xy. Let's just keep things simple. And if v xy is equal to u xy minus 10, minus 100, let's say. This is, let's say, part 1. Part 2 is vxy is equal to. So some of these questions are actually from Radian. You can go and check it out if you like. This is, say, log to the base 10. Or you can also take it as natural log. Why are we taking base 10? Of log of u. And let's say is equal to 1 upon u. Let's say we take these 3 examples just to make sure that the idea is actually clear. So what do you think is going to happen? Which one of these is going to be like having the same ordering over consumption bundles, and which one will not be having the same, if any? You can think and then answer. Okay, somebody has answered. Okay, anybody else wants to try? So we're just trying to see what kind of a transformation it is. So if you have three numbers, 5, 10, and 15, and you subtract 2 from all of these numbers, you still get the same ranking, right? You get 3, 8, and 12, which is again in the same order. It's not, obviously, it's not the same kind of number. It's not even like a multiple of the same number, but oh God, but it is the same ordering. So I think when my iPad goes on standby, the whole thing disconnects. Just give me a minute again. This must be like the fifth time I'm logging in at least. So I'm sorry about that. It's just some technical issue with this thing. Okay. So, like I was saying, in this particular situation, you've just subtracted the same constant number from the function. So for all values of that function, if you subtract the same number and it's a positive number, then obviously you get the same ranking of consumption bundles, right? So this is fine. This is having the same ordering. Then we come to log of u, and we know that logarithm is obviously a positive monotonic transformation. So even if you take log of some number or numbers, the value of the log will obviously be very different from the number itself, but the ranking or the, the values will be still in the same order. That is why many times when we take graphs and we draw diagrams which have a lot of wide range, if some variable is varying from say 1 to 100,000, instead of drawing a graph which shows 1 to 100,000, we take logarithm of it and then we draw it, because it doesn't alter the ranking, it just obviously helps you adjust the scale. So that means logarithm is also fine. It is not altering the ranking. The next is reciprocal. Reciprocal means like if you have ranking of numbers, say 5, 10, and 15, reciprocal means it's 1 by 5, 1 by 10, and 1 by 15, which means that the first one is the biggest, the last one is the largest, the smallest. And as you can see, that is the opposite of the initial ranking, right? 5, 10, and 15 is in increasing order, whereas 1 by 5 to 1 by 15 is in decreasing order. So this is not going to work. And reciprocal of a function is not a monotonic transformation. Okay, so these are just some extra examples I thought I'll take to illustrate the concept in case it is not so clear. Oops. let's go back to our question. So, yeah, now we come to something called marginal rate of substitution. And I think we will need to spend a little more time on this. So I will try to finish this today, but in case this, this whole concept is a bit foggy, I'll explain it in more detail in the next time. But we will discuss it today also. So we are given that Simon's utility function is x plus 2y whole square. Okay. So first of all, the question is, are x and y substitutes? And then is you are asked to calculate the MRS, and then you're asked, like, if this this is true, if Simon is willing to give up 2 units of y to obtain 1 unit of x at this, to remain at the same utility level. So I'll give you a few minutes to think over it. We don't have that much time left, but we have enough time. So please think and calculate the MRS, and then I'll discuss it. Okay, let's solve this question. Let me see what you answered. Okay, let's see. I also don't remember the answer. 1 minute, I lost the question. Give me a minute. Right, so we are given, this is question 8, given u of x, y is x plus 2y whole square. And you are asked, okay, firstly, we'll come to whether x and y are substitutes or not. First, let's calculate the MRS, right? MRS is what you're basically asked in this. So how do we calculate MRS? MRS is nothing but minus marginal utility with respect to x upon marginal utility with respect to y. So how do we calculate marginal utility? We just take a partial derivative. So you're going to be using a lot of calculus in this part and in some other parts of the course as well. So let's calculate marginal utility. Ux is nothing but partial derivative of the function u with respect to x. That's why we have the subscript x, small x. Okay, so this is nothing but 2x plus 2y, right? And then we take uy, which is del u by del y, which is again, you calculate this, 2 comes here and becomes 4, this becomes x plus 2y, right? So you have MRS is equal to minus ux by uy is equal to minus 2x plus 2y upon 4x plus 2y. This gets cancelled, you get minus half. Okay, so this is fairly straightforward, and that is, I think, one of the where's the question? Yeah. So that is option C. MRS is minus 0.5. And now in this particular function where you are given u is x plus 2y whole square, if you take the function b as some other utility function, x plus 2y, then u of x plus y is nothing but vx comma y whole square, right? And in this function v, which is x plus 2y, you can see that x and y are substitutes. They're not perfect substitutes. You don't value both the goods equally, but you do, you can substitute one good for another to achieve same utility level as you had before, right? So in this particular case, it is not like you can give up 1 unit of x and gain 1 unit of y to remain at the same utility level. But if you want to do the maths, we can do it something like this: bx comma y, say, is equal to k. If I subtract epsilon from x, then how do we get back the same function? Y minus half epsilon. Let's rewrite it like this: epsilon by 2. That comes out to be the same function, right? X plus 2y. K is some value of utility, right? So if you are initially at a value of utility, not minus, sorry, what this is plus. Yeah. So if you give up 1 unit of x or 1 quantum of x, you you gain basically 2 units of y, something like that. It is not, let me see what the option says in your case. Yeah, so it is the other way around. In this case, option D says Simon is willing to give up 2 units of y to obtain 1 unit of x to remain at constant utility level, whereas it's the other way around. Why? Because first of all, the function itself is x plus 2y, means y is being valued a little bit more, right? So you will give up 2 units of y to gain 2 units of x to gain 1 unit of Y to remain at the same utility level. It's the opposite of what is given as the answer in your option D. So option D is not correct. The opposite of option D is actually correct. Right? Did everyone get this answer? So yes, A and C are the correct answers. Okay, let's go to the next question. This question, we can solve it today, but it's a slightly tricky question because I want to explain these things in a little bit more detail. The same marginal rate of substitution concept about when you're giving up one good for gaining equal quantity of the other and vice versa. So that is why this question is designed to be a little bit confusing. So, so I will leave this question for you. I want you to spend a little bit of time to think about it instead of me just answering it in 2 minutes. So please take some time and solve this question. I actually wanted this question to be like homework. I mean, it's not like you have like to submit the answer or something. Oh God, what the hell is this now? I don't want AI. Just go to hell. Okay, so I will upload these slides as always. Please attempt this question on your own, and then we will compare answers in the beginning of the next class. Okay, and you have an updated list of references. You can refer to the 2 extra books which I think I've added here, maybe 1 extra book. Most of these books have covered this subject pretty all right. I think in the first one, Core Econ, you may find some interactive graphs also. I don't remember very well, but I think it has some interactive graphs. And if you, I mean, if it helps you understand, you can play around with those and see if it's useful. So I'll end the class here today and I'll upload these slides as usual. And whatever your answer is, keep it with you. I will ask you your answer in the beginning of the next class, and then we'll discuss which is what. Okay. All right, so I'll end the class here. Thank you everyone for joining, and I'll see you next week.